Do it now.
Will be yes, it's working. So shall we start?
Yes.
Yeah, I'm ready.
Okay. So thanks everybody for coming. This week we are very happy to have Sal Pace from MIT talking about lattice T-duality from non-invertible symmetries in quantum spin chain. Go ahead.
Awesome. Yeah, so thanks for the invitation. I'm happy that Symmetry Seminar is back up and running. There's a few months where there was like a hole in my life because there wasn't a weekly Symmetry Seminar to go to. And I'm happy to be talking about recent work with two wonderful collaborators. Arco, who's currently a grad student at MIT and starting a postdoc at Stony Brook in the fall in Shuheng. And I want to start the story with dualities. What are dualities? Dualities are maps between two seemingly distinct theories that turn out to secretly be the same. And they're both conceptually useful and practically useful. They tell us about the way that we organize theories shouldn't be based off of Hamiltonians and Lagrangians and degrees of freedom. And they also tell us that sometimes something that's hard to compute becomes easy to compute after you do a duality transformation. And if you go to someone on the street and you ask them what their favorite duality, you'll hear a bunch of different things. The person on the street may say T-duality. They may say level rank duality. They may say particle vortex duality. They may say Kramers-Wanier duality, etc. And you get very confused when you ask them, well, what are these dualities? How are they related to one another? And the confusion arises because these are just not the same notion of duality. We have to be more precise what we mean when we say two things are the same. So these examples of duality falls into three different types of duality. Now, certainly more than just three. I'm just going to focus on these three. The first is exact duality. An exact duality relates two different presentations of the same quantum systems. They're true to God the same. Everything about them is the same. Every single state in one quantum system is in the other quantum system. Every operator is in the other one. Every symmetry is in the other one. It's an isomorphism of the theories. And there's many examples. The T-duality example we saw is of this type. S-duality, so normal electromagnetic dualities of this type. Level rank duality is also of this type. Another type is IR duality. So now we have two quantum systems and they're distinct in the UV, but they happen to flow to the same quantum system in the IR. So examples of this are like particle vortex duality and dualities in supersymmetric gauge theories like Seiberg duality. And then the third type that the person on the street told us about is discrete gauging, or sometimes called orbifolding. So discrete gauging, it relates two distinct quantum systems, and it relates them by gauging a discrete symmetry. These quantum systems are going to generally be distinct both in the UV and in the IR. But there's something we gain by doing this is that when we gauge a discrete symmetry, we tend to only change the global stuff. So we can end up learning about one theory by considering this other theory. And examples of this are like Kramers-Wanier duality, bosonization, and fermionization. And talking to people about discrete gauging, I often come across very confusing statements. And I want to, set my understanding clear. And my understanding is that discrete gauging generally is totally unrelated to both exact duality and IR duality. So the typical scenario is on the left. I have some theory. I'm labeling it by a Lagrangian, but it doesn't need to be labeled by a Lagrangian. And maybe it's exactly dual or IR dual to some other theory. But also maybe I could do some gauging and go to a theory L3. Generally L2
Sorry, could I ask
L3.
Could I ask a question?
Yeah, of course.
Bosonization. I think of bosonization as an exact rewriting of one theory in terms of another. I mean, you can even
Here I'm
even
just
express the fields. I mean, maybe it's not a big deal. It's probably not that essential to your talk, but I can express, the fields in a bosonic formulation and in a fermionic formulation. I can exactly match the correlators. Isn't that an exact duality? In your
yes. So
class.
here by bosonization, I mean I start with a theory that has a fermion number parity and I gauge it. So maybe I start with some Majorana
That's what I would call
CMP.
bosonization. Okay, that's fine.
Yeah, that's my definition of bosonization. Yeah. Yes. Sorry, I wasn't
The
clear on
same
that.
comment applies to Kramer-Wanier duality.
I think the way I interpret what you said is that some people use the gauging as you just gauge it rather than perform duality. And if you're careless, you treat them the same, and then the two theories are not exactly the same.
Mhm.
As far as I can tell, Kramer-Vanier duality is an exact rewriting of the same theory, just like bosonization. And if you're careless about interpreting it, you might be led to think that they're not exactly the same.
Yeah, again, here when I say Kermes-Rodney duality, I mean gauging a Z2 zero form symmetry in 1 plus 1D. These aren't necessarily my words. I didn't come up with these words. This is how I see other people using these words.
But there are also other people who say that if you gauge and
I know.
also change the value of the temperature from above the transition to below the transition, then it's an exact rewriting. But keep going, I'm sorry.
I'm not responsible for these other people. Okay, so the typical scenario is on the left, and there's a special case, and that special case happens to be when L2 and L3 are the same. In that case, the exactor IR duality transformation maps you to the same theory as the gauging map does. But importantly, these are two different maps. For example, if it was an exact duality, it's bijective. If it was discrete gauging, it has a kernel, so it's certainly not bijective. Okay. So let's see this in action, and let's see it in the context of T-duality, which is the subject of this talk. So we have the compact boson CFT. It's at some radius r, and the Lagrangian is as follows, where big phi is a compact boson. And it's well known that there are two U1 symmetries. There's a momentum symmetry, sometimes also called a charge symmetry, and there's a winding symmetry, sometimes also called a vorticity symmetry. And the occurrence is as follows. And T-duality is an isomorphism between the theory at radius r and the theory at radius 1 over r. And the T-duality map, at least for the three symbols we have on the screen, is Lagrangian at radius r goes to 1 over r. The momentum current goes to the winding current, and the winding current goes to the momentum current. So the two U1 symmetries on the left get exchanged under the T-duality map. But both theories have the same symmetry content. So there's also discrete symmetries in the compact boson CFT, and we can gauge them. So for example, the U1 momentum symmetry has a discrete subgroup described by Zn, and we can gauge it, and we can have a map between the compact boson at radius r and the compact boson at radius r divided by n. And we can see how the momentum and winding currents get transformed under this map. And the momentum current, this picks up an n, the winding current gets divided by n. And importantly, because we're gauging a symmetry, any states that are charged under the symmetry will get projected out. So this map has a non-trivial kernel. It's spanned by all states whose momentum charge isn't an integer multiple of n. Okay. So for general radius, in particular, radius is not equal to square root of n, the image of the Lagrangian under T-duality and gauging is different. So this is the typical scenario I showed on the last slide. You start with your theory at radius r, you do T-duality. Now your presentation is the radius is flipped. If I were to start with my theory and gauge, I would go to a completely different CFT. But when the radius is equal to square root of n, we have a special scenario because r divided by n is the same as 1 over r. Okay. And for these radii, it's useful to view T-duality as an isomorphism of the compact boson CFT and its Zn momentum gauge theory. You also get something else in this scenario. You actually get a non-invertible symmetry. And the non-invertible symmetry, you can just see it on the diagram here. For example, we could first gauge Zn momentum, and then we can implement T-duality, and we come back to where we started. So if we follow how, for example, the winding and momentum currents transform under this non-invertible symmetry, first they pick up factors of n and 1 over n under the gauging map, and then they get exchanged under the T-duality map. So this non-invertible symmetry would send the momentum charge or current to n times the winding charge or current, and so on. And this non-invertible symmetry provides a more invariant view of T-duality at this radius. In particular, the existence of the U1 momentum and the U1 winding symmetries and this non-invertible symmetry is a symmetry based in invariant definition of T-duality. If T-duality didn't exist, you could not have this non-invertible symmetry. And this is a perspective that will be useful for us when we start to go on the lattice. Okay. So that's T-duality in the continuum. And it's natural to ask if T-duality also can exist in lattice models that flow to this CFT in their IR. Okay, why may you want to ask this? Well, maybe you're a person who cares about the lattice, who holds models of qubits in high regard, and you just want to know if that's possible to exist in your favorite lattice models. Or maybe you're someone who cares about field theory, and you understand there's a mutualistic relationship between understanding theories on the lattice and understanding theories in the continuum. As we learn more about theories on the lattice, we're naturally guided to learning more about the continuum theory. And there's an answer to this that's already known, and it's yes. They exist in what's called modified Verlaine models. And I just want to give a flavor of what this lattice regularization of the compact boson CFT is. If you really wanted to describe the compact boson CFT globally, here's one way to do it. We take spacetime and we put a bunch of patches, open contractible patches on spacetime. And we can describe our compact boson by having a real valued field corresponding to each patch, I, J, and K. And on their overlap, we have an integer such that the difference between the fields on their overlap between patches is 2 pi times this integer. And what's nice about this is it gives rise to a gauge redundancy. I can shift phi by 2 pi times some integer m, and then shift n by their difference, and it doesn't change this overlap rule. So in a sense, this gauge redundancy compactifies R back down to the circle, so I have a compact boson I wanted to start with. Okay, so what is this Verlaine model regularization? Well, I take these patches and I kind of shrink the patches to points. So when I do that, and now I have a space-time lattice, I shrunk my patches to points, so now I have a real scalar on each point, and now the overlap is just a link, and that's where an integer valued lattice field lives. And I still have this gauge redundancy, namely that phi and n are related as follows. And I can write down a nice space-time lattice model using these degrees of freedom. I can see T-duality exactly in the space-time lattice model. I can also write down a Hamiltonian formalism, see T-duality there. And the Hamiltonian formalism will have infinite dimensional local Hilbert spaces because of this n being z valued. Okay. So the answer is known, but then you may start to wonder, well, that lattice model looked quite similar to the compact boson CFT. What about lattice models that have no resemblance to the compact boson CFT? And what about the simplest type of such quantum lattice models, which are just made of qubits? Qubits on sites with a tensor product factorized Hilbert space. So that's the subject of this talk. We're going to focus on the what's called the XX model. And we'll find that there's a non-invertible symmetry and a corresponding lattice T-duality in the XX model. And along the way, we'll encounter a U1 lattice winding symmetry, and we'll find that there's a extensively large Lie algebra belonging to this winding symmetry called the Onsager algebra. And by studying this, we'll actually prove not only that some of the 't Hooft anomalies that exist in the CFT exist on the lattice, but we'll show that there's a gaplessness constraint on the lattice, just like there is in the CFT due to the perturbative anomalies. And finally, we have all these new symmetries. We can say, well, I start with my XX model and I deform it in a way that preserves these symmetries. What do I get? Well, because of this gaplessness constraint, I have to get something that's gapless. And we can construct interesting phase diagrams where everything in the phase is gapless. So that's the roadmap for the talk. And we'll start this by reviewing what the XX model is. So we have a 1 + 1D quantum lattice model. Time is continuous, and space will be a finite ring with L lattice sites, and there's a qubit on each site J. And throughout the talk, I'll always assume that the number of lattice sites L is even. Okay? And I'll denote the Pauli operators by X, Y, and Z, and I'll always assume that they have the following periodic boundary conditions. So the Hamiltonian for the XX model is as follows. And sometimes this Hamiltonian is called the XY model, just because there's an X and a Y here. More generally, I think people say the XY model when there's a coefficient here, and the XX model is named to signify that the coefficient on the X and the Y term is the same. Okay. So here's our model. And there's a well-known symmetry of this model. In fact, there's many symmetries of this model, but there's one that we care about the most that's known already, which is a spin rotation symmetry, U1M. And it's easy to see that it commutes with the Hamiltonian if I just rewrite the Hamiltonian in terms of the lowering and raising spin operators. This unitary operator acts on the raising and lowering operators by a phase, which is manifestly leaving this Hamiltonian invariant. Okay. So why am I considering the XX model? Well, it's simple. Also, the IR of the XX model is known to be described by the compact boson CFT at radius square root of 2. And if you've forgotten my, factors of 2 and pi's in the Lagrangian, R equals 1 is the self-dual radius. So, okay, what do I mean by the IR? Well, what I really mean is we take our XX model and we focus on the low energy states within some order 1 energy window above the ground state. And then we take the thermodynamic limit. And if we do this procedure, we can relate operators on the lattice to operators in the CFT. So for example, the raising operator gets related to this primary field, maybe with some number in front, which is not important to us. And then the QM, the lattice charge, gets related to the momentum charge of the CFT. This explains why I have this superscript M. QM generates a U1 lattice momentum symmetry. It's a U1 symmetry on the lattice that exactly becomes the U1 symmetry, momentum symmetry in the CFT. So we know that the XX model flows through the compact boson CFT. We know there's a momentum symmetry. It's then natural to wonder, well, what else does the XX model have that we know of in the compact boson CFT? Does the XX model have a lattice T-duality? So to approach this, let's recall that in the IR, T-duality, because the radius is square root of an integer, will implement an isomorphism between the CFT and its, in this case, Z2 momentum gauge theory. Okay, so we know that this is true in the IR, so let's use this as a motivation. And the motivation will lead us to now gauge the Z2 momentum lattice symmetry. So if you just set the angle equal to pi that I had in the last slide, this is what the operator can be rewritten as. It's some nice on-site symmetry. This -1 to the j will just lead to an overall plus sign or an overall minus sign, depending if L is 0 mod 4 or 2 mod 4. And we can gauge it in the way that we normally gauge symmetries on the lattice. And I'm going to be quite brief with this. And I'll just summarize the gauging by how to relate the qubit model before gauging to the qubit model after gauging. So this is the relation. This to say what's under the hood, if people don't like this notation. I start off with this symmetry and I introduce new qubits on the links. And the new qubits on the links will be related to the original qubits on the links by a Gauss law. Then I'll go to a unitary frame where the initial qubits on the links are polarized and decouple out. So I'm only left with qubits on links. And then I can shift the qubits from the links to the sites. So I start off with a model with qubits on sites. I end up with a model with qubits on sites. They're different models. And I can relate these two models by the following map on their operators. This looks just like the Kramers-Wannier transformation of the transverse field Ising model. The only difference that actually has substance is now there's a -1 to the j here. This because there's a -1 to the j here. And if you apply this map to the XX model, you'll find that its gauged Hamiltonian is the following. And if you're familiar in the study of SPTs, this is the interpolation point between two Z2 times Z2 SPTs in 1 + 1D. This first term is the paramagnet term. The second term is the cluster state term. Now, what's more interesting for us is the fact that if you, for instance, look at the spectrum of this Hamiltonian, you'll actually see that this Hamiltonian and the XX model Hamiltonian are unitarily related. There's some unitary, I'll call it UT, and it implements an isomorphism between the XX model and a Z2M gauge theory. And the unitary operator itself is pretty typical looking. It's just some finite depth circuit. There's some control Z gates. There's gates that rotate the spins. And it acts on the Pauli operators in a pretty typical way. Now, what's more interesting for us is not the exact details of this unitary. It's the fact that the existence of this unitary implies there's a non-invertible symmetry. And this non-invertible symmetry works just like it did in the CFT. We do the gauging map, and then we do some isomorphism to go back to the theory we started with. And I won't spare you. I won't show all the details of the non-invertible symmetry. Let me just show what matters to convince you that it's a symmetry of the XX model. So let's see how it acts on product of nearest neighbor X operators and product of nearest neighbor Y operators. And all it does is it sends it to XX and YYs in a way that just shuffles the terms in the XX model and leaves it invariant. Now, for people who've studied the compact boson CFT, you know that there's an S1 family of Tambari-Yamagami fusion category symmetries. And this non-invertible symmetry that we saw in the compact boson CFT is just one member of this family. Well, how do you get other members of this family? You just take your non-invertible symmetry and you multiply it by U1 symmetry operators. And the same thing applies here. You can take D and multiply it by continuous U1 symmetry operators and create and generate the same S1 family of operators in the lattice. You can figure out exactly which operators to multiply D by, this by studying the fusion rules of the operator D. And you could replicate this S1 family of Tambari-Yamagami fusion category symmetries directly in the XX model. Okay. So we see we have the non-invertible symmetry. We see we have this isomorphism between the XX model and the Z2M gauge theory. Is this enough to declare victory? Can we now say, oh, I now have a lattice T-duality? Well, we're missing something. What about the winding symmetry, right? Okay, that's fine. Recall in the compact boson CFT, if I transform the momentum current by the non-invertible symmetry, I would get the winding current with some important factor out in front. Well, let's do that on the lattice. If we act D on the lattice momentum charge, we get the following. We get a factor of 2 times some operator QW. And this operator is integer quantized. And it relies on the fact that L is even. Now, we know that QM becomes the momentum charge in the IR. And we know that this non-invertible symmetry also becomes one of the non-invertible symmetries in the IR that exchanges QM and QW. Therefore, we know that this QW has to go to the lattice winding charge has to go to the continuum winding charge along the RG flow. This is the lattice winding charge that we were looking for. To also make it clear, if we then act D on QW, we get the same relation that we do in the continuum. QW becomes 1/2 QM. So now we can declare victory. Now we can say, good, the XX model has a lattice T-duality, and here's our evidence. There's an isomorphism between the XX model and Z2M gauged model. There are conserved momentum and winding charges on the lattice. And there's non-invertible symmetry that exchanges them with the correct factors of 2 and 1/2. Okay.
Sorry, can I ask a question?
So are there any questions? Yeah, please.
What are the lattice operators that are charged under QW?
They're a little bit complicated. I didn't write them down. They're not easy to say in words, but they're in our paper.
Okay.
Can I ask another question?
Yeah, please.
If you have the momentum symmetry, like at least in the continuum, the way it works is instead of gauging a discrete subgroup, you discrete a trivial subgroup, and that way you prove the duality. Can you do the same sort of thing in the lattice? Like instead of gauging the set 2, then impose that the gauge fields are like trivial, and then you don't need
What do you mean by gauging a trivial subgroup?
You add the couplings as if you're going to gauge, then you add a Lagrange multiplier telling you that the gauge field is actually trivial. But then you do the integral. This is how you prove the duality normally. So I'm asking if it's possible to tackle it this way in the lattice.
Yeah, you can do it that way with the modified Villain formalism. I don't know how to do it in this lattice model, though. Yeah. And just be clear, you're just saying the normal way that we can show T-duality quickly is we just mess around with the path integral, massage how we're integrating things, introduce Lagrange multipliers, and then we see if we integrate out some fields, we get the compact boson CFT with 1 over R instead of R. Yeah, I don't know how to do it with this qubit lattice model.
Could you remind us what squared is? What D squared is?
T
Can you
squared?
D squared.
Oh. Yeah, yeah, good. This is what D squared is.
So the kernel is the odd states with odd to QM, is that right?
Exactly, you're exactly right.
That's the kernel of D, or just D squared?
Yeah, that's right. Which is something you should expect because we constructed D by using the gauging map for the Z2 momentum symmetry. Good. Any other questions? Okay. So things are looking a lot like they do in the continuum. But now let's notice something that departs us from our continuum intuition. So in the continuum, we have a U1 momentum, a U1 winding, and their symmetry group is just a product group, which is to say that the charges commute. Is this true on the lattice? And the answer is no. You can just look at the explicit expressions I gave you a few slides ago, and you'll see they don't commute. But that's okay. It's entirely consistent that they don't commute on the lattice, but in the IR limit, they do commute. And this is something you can check. You can literally take the XX model and act QM and QW on the low-lying states and see that their commutator goes like 1 over L. So in the thermodynamic limit, it goes to 0. Okay. So if they don't commute, well, what's the algebra describing? Well, it turns out they generate what's called the Onsager algebra. And this is an algebra that Onsager used when he introduced his solution to the Ising model. He didn't introduce it as a symmetry. He introduced it when he was when he was expressing the transfer matrix. So this Onsager algebra, it's formed by an extensive number of conserved charges. I'll label them by Qn and Gn. And n is some integer. And it's related to the momentum and winding symmetries as follows. Q0 is this momentum charge, and Q1 is 2 times the winding charge. This factor of 2 here is just purely for some convenience later on. Okay. And it turned out they generate the following algebra, which is the Onsager algebra. And you can see that they generate this algebra as follows. Start with n equals 0 and m equals 1. That will give us G1. Now we can go down here. Maybe have n equals 1. We just have G1, so m is equal to 1. Well, this is G0 when n and m are both equal to 1. We know what Q0 is. And then this will be Q2. So now we find Q2. And we can play similar games to generate all the Qn's and all the Gn's. Now, if you also look at this algebra, you can use the fact that in the IR limit, Q0 and Q1 commute to easily show that in the IR limit, n only depends on its even or oddness. So when n is odd, it flows to 2 times the winding charge. And when n is even, it flows to just the momentum charge. And furthermore, because the momentum and the winding charge commute, you can show that Gn will always flow to 0 in the IR limit. So it's interesting if you stare at these charges for a while and compare and study how other symmetries of the X model act on them, you'll find that the algebra is much richer than just the Onsager algebra. So for example, I'm just showing the Qn charges here. And we can say, well, the XX model has translation symmetry. How do translations act on these Qs? Well, it acts in the following way. It kind of reflects this lattice of Q charges about the 0 point. Okay, then you can look at, well, how does the non-invertible symmetry operator D act on these charges? Well, now it reflects it about like the 1/2 point. Okay. And actually, we can see why D implemented the lattice T-duality, the non-invertible related to lattice T-duality. By looking at this, it exchanges Q0 and Q1. And remember, Q0 was momentum charge and Q1 was 2 times the winding charge. And then you can look at other operators too. For example, if you start multiplying D by the momentum symmetry operators or the winding symmetry operators, you can just directly go between the different charges. It's a little highway going between. Okay. very algebraically rich. It's very different from the compact boson CFT. But let's keep on going with the spirit of trying to find more things that are similar to the compact boson CFT in the XX model.
Or can I ask a question?
Yeah,
Are all these charges local?
good. So as n gets larger, the charge itself will also get larger.
Okay, I see.
So as long as n is order 1, it's local. If n is order, the system size is non-local.
I see.
You know, I'm refraining myself from calling this a symmetry. I don't want to view it necessarily as a symmetry. I just want to view these as some conserved charges, and some of them correspond to nice local charges.
But so are all these charges coming from the fact that the XX model is integrable?
I think it's related to that fact. I don't have anything deeper to say than that, though.
Okay, thanks.
Okay. Good. So while we were searching for the lattice T-duality, we just found a bunch of symmetries in the XX model. And these symmetries are directly related to those in the IR.
Well, sorry, related
So
to
then we
this
can ask,
question, are they other charges higher spin? I mean, is there some sense? I guess it's not relativistic. Is there a sense in which these are higher spin charges?
yeah, I don't know how to. Yeah, that's a great question. I don't know how to think of that in this model of qubits. And also, since most of them just flow to the momentum and winding charges in the continuum, I don't know how to use the continuum to answer that question either. So I'm not sure, but it's an interesting question.
I have a perhaps related question. If the model is integrable, it has an infinite number of conserved charges. What's the relation between this algebra and the conserved charges of integrability?
Yeah, I don't know. I don't exactly know the relation. Yeah, I don't know. Those charges, most of them are totally non-local. You know, the way I know how to think of those charges is to Fermionize the model, go to momentum space, and you just have particle number conserved at each point in momentum space. And then you could bosonize those and bring those back. I don't know how to express these charges in terms of those charges.
Okay, so you just started answering my second question, which this model is really free, right? So we can diagonalize the Hamiltonian and we have particles with all sorts of momenta. So there's a huge symmetry, taking any momentum and multiply that state by an arbitrary phase. What does this have to do with your symmetry? Your symmetry is probably a subgroup of that.
Yeah, you know, certainly. I like I said, though, I don't know exactly how to relate the two. Yeah.
So if I may comment,
Yeah, please.
so there is so I think all of the momentum occupation numbers can be, you can take a linear superposition of them to get these kinds of charges. So it's not really, each one of them is non-local, but there is a linear superposition that is more and more non-local as you go.
Okay.
Okay.
Yeah, thanks for the comment. Okay. Good. Yeah, we're gonna start thinking of anomalies. Yeah, and because we found all these symmetries that are directly related to those in the IR, it's then natural to ask, how do these symmetries match the anomalies in the IR? You know, and I really wanted to consider the following symmetry operators. I want to consider the Z2 operator, which corresponds to the Z2 momentum symmetry. The U1 winding symmetry operator. And there's also a Z2 symmetry operator we haven't talked about, which is product of x's. This clearly commutes with the Hamiltonian, which is just x times x plus y times y. And what's nice about these symmetries is they form a very simple group. Namely, even though Q momentum and Q winding don't commute, these operators do commute. So there's just a product group of Z2M times U1 winding. And because QW had single y's in it, when we act C on the U1 operator, we'll flip the sign of the angle theta. So then this is why there's a semi-direct product structure. And what's nice about this group is it's a subgroup both of the UV symmetry and the IR symmetry groups. So then we can compare their anomalies directly. And if we do that, what we find the following. Firstly, there's a type 3 anomaly between the Z2C, Z2M, and Z2 winding subsymmetry. And the way that this manifests in the lattice is the same way it manifests in the continuum. Namely, if I insert a symmetry defect of one of these Z2s, the other two Z2s furnish a projective representation. Furthermore, we can look at this mixed anomaly, and it also manifests in the same way as it does in the continuum too. Namely, if I insert a U1 winding symmetry defect, and I have the angle theta go from theta to theta plus 2 pi, it'll flip the sign of all the Z2M charges. So even start charges will go to odd charge states will go to even. And this is exactly spectral flow. It's not spectral flow for the most general case where this is a U1, but it's a spectral flow for the case where it's a Z2. What I want to focus more on in this talk is something a bit different, which is that in the continuum, we have a mixed anomaly between U1 momentum and U1 winding, which is a perturbative anomaly. And a consequence of that, namely the fact that the perturbative anomaly is encoded in the local OPE data, is that the anomaly can't be matched by a gap phase. So in that sense, it enforces gaplessness. So then it's interesting to wonder, well, I have these lattice momentum and winding symmetries. Do they also enforce gaplessness? There's a other way to phrase this. From the view that anomalies prevent trivial gapped phases, or SPTs, we can say, well, does the on-figure algebra match the perturbative anomaly in the continuum? And the answer is yes, and we're going to show it by Fermionizing the XX model. So to Fermionize the XX model, we'll do so by gauging the Z2 momentum symmetry, but we won't introduce qubits on the links. We'll actually introduce complex fermion operators. And this is inspired by the way that we think of gauging in, how we think of fermionizing in the field theory context, where we gauge some Z2 symmetry, but in a way where it couples to the spin structure that we've put on our orientable 2 manifold, which is based on. Now here, I think when lattice people think of fermionizing, I think they have a tendency to think of some Jordan-Wigner transformation. But Jordan-Wigner transformations come with the cost that if it's on a finite ring, there's a term at the end which is not as nice looking as you wanted it to. This is really the more precise way to fermionize a qubit model that gives a local Hamiltonian to a different local Hamiltonian. Okay. So to write down the gauging procedure, it's actually more convenient to express the complex operators in terms of real fermions, these Majorana as A and B. And they satisfy the normal anti-commutation relations. And then using those, we can then define the Gauss law that implements the gauging. And again, just like for the Z2 momentum gauging case, we can now do some unitary transformation that will polarize the qubits on the sites such that they decouple out, and we're left with a model only in terms of fermions. And we could summarize the effect of that unitary transformation and the map from the qubit model to the fermionic model just as follows. The operator Z gets replaced with I times AJ BJ, which is to say that, remember, the Z2 momentum symmetry was a product of the Z operators with a sign sometimes. So the Z2 momentum symmetry after fermionizing becomes the fermion number parity symmetry of the fermionic model. And this XX operator goes to some fermion bilinear depending on if it's odd or even. So if you apply this map to our XX model, what do you find? Well, the XX model becomes this 2 Majorana chain, which is, if you write it in terms of complex fermion operators, is some nearest neighbor hopping Hamiltonian. And this nearest neighbor hopping Hamiltonian in the IR is described by the Dirac CFT. And that's totally consistent with the fact that if I fermionize the compact boson at r equals root 2, I end up landing on the Dirac CFT. We can also track what happens to our lattice momentum and lattice winding charges. The momentum charge becomes some integer quantized charge. I'll label it by QV because in the IR, it'll become the vector symmetry of the Dirac CFT. Similarly, with an important factor of 2, the winding symmetry will become a lattice axial symmetry. It's an axial symmetry because in the IR, it flows through the U1 axial symmetry of the Drach CFT. And just like how QM and QW didn't commute in the XX model, QV and QA also do not commute in this Majorana chain. Okay, so why are we fermionizing? Well, we're fermionizing because it's now quite, it's easy to now write this most general local Hamiltonian that commutes with the QV and the QA operators. And let me just sketch the derivation of this general Hamiltonian. The first step is that we'll assume that the Hamiltonian is local. So n is sum over some label set we haven't specified yet. These g's are coupling constants, and hj is some Hamiltonian acting only in some finite patch centered at the site j. So if we want this Hamiltonian to commute with the U1 vector and U1 axial lattice symmetries, well, for one, we need to commute with this operator. This is certainly an allowed operator in this lattice symmetry. And what's nice about this operator is it acts on the Majoranas in a fairly simple way. It just shifts the A Majoranas to the left and the B Majoranas to the right. Okay. So what does that imply? Well, for one, it implies that this Hamiltonian, because it's local, can't have terms that mix A and B. For example, if I have an A at site J and a B at site, K, and I apply this, they'll spread out by 1. So if I wanted to symmetrize this, now it's sum over its orbit, and I would end up having grossly non-local terms. So I need to have terms that are only of A's and only of B's. And furthermore, because after we decide that, then if I apply this, it tells me that the Hamiltonian has to be invariant under translating only the A Majoranas and also translating only the B Majoranas. So it's a translationally invariant Hamiltonian, so these coupling constants G don't depend on the site label J. Okay. Now we consider another part of the lattice symmetry, which is just a general U1 vector transformation. And if you explicitly calculate the transformation using the charge I showed you on the last slide, the A Majorana gets transformed as follows, and the B Majorana also gets transformed in a similar way. Well, what does this tell you? Well, for one, it tells you that you can only have quadratic terms in your Hamiltonian. For example, if I had an A times A times A, and I do this transformation, I'm going to end up getting some terms that mix A and B, and that certainly won't be symmetric with the first bullet point. However, for a quadratic term, you can use this normal trig identities and show that it's invariant. If you add the A's and the B's together exactly in this way. So just by considering these two symmetry transformations, we showed that the most general term in this local Hamiltonian is of this type. It's still quadratic, and it just couples the Majorana at site J to a Majorana at site J plus N. If we put it together, this is our general family of Hamiltonians. And now if we want this to be local, N is only going to sum over some finite label set such that N is never the scale of the system size.
Hughes and Sal?
And what's... Yes. Hey,
Can I ask a quick question about the previous slide?
Yeah, please.
Can you remind me how you argue that the Hamiltonian has to only contain quadratic terms?
Yeah, so so in the paper, it's much more detailed, but the argument went as following. Suppose I had a term that was like A at site J, A at site K, A at site L. And we do this transformation. And let's assume that phi is very, very small. So we can linearize, so it's just a linear, so cosine goes away and this is linearized. The problem is that this A times A times A term will get transformed to terms that now have B's as well.
Right.
And if that's, if that's the case, certainly that can't be another term that exists somewhere else in the Hamiltonian because of this first requirement. The A's and the B's can't mix.
I see. But if I only use invariance under QV, and that's just charge conservation, right? So I should be able to write like density coupling, but somehow that violates the other symmetry. That what you're saying? Yeah.
That's right. Yeah, the density coupling would even just having a mass term like C dagger C at the same site That would end
Okay.
up violating the axial symmetry. That's exactly right.
Okay, I see. Thank you.
You're welcome. Yeah. Okay. Good. So this is our family of vector and axial symmetric Hamiltonians. And it's quadratic. We can exactly solve it. And it's easy to see that it's always gapless for all choices of G. Briefly put, if you go to momentum space, you just have some decoupled oscillators or not oscillators, but decoupled fermions at each momentum. And this dispersion is just a sum of signs, and there's always going to be zeros. So the ground state will always have, omega less than 0 states filled, omega greater than 0 states unfilled, and there'll always be these zeros where the gapless modes live. Good. So we just showed that the lattice axial and the lattice vector symmetries enforce gaplessness. What does this have to do with the XX model? Well, now we can use bosonization. And bosonization will provide a one-to-one correspondence between this family of Hamiltonians and qubit models that commute with both the lattice momentum and the lattice winding symmetries. And because by here, bosonization means we're gauging the fermion number parity symmetry, which is a discrete gauging. If the family of fermionic Hamiltonians are gapless, then any qubit model I'll get by bosonizing will also be gapless. Therefore, we find that the momentum and the winding symmetries enforce gaplessness. Alternatively, we can phrase this as the perturbative anomaly of the compact boson CFT is matched by the Onsager algebra. And there's actually an interesting corollary of this. So if we consider L equals 0 mod 4, just briefly, we can find a unitary transformation after which the momentum and the winding symmetries become very simple looking. There's a sum of z's and a sum of x times x's. What does that mean? Well, any qubit model with L equals 0 mod 4 sites that commutes with a sum of z and sum of x times x must also be gapless. And then you can conjecture this is true for all system sizes, whether or not L is 0 mod 4 or 2 mod 4, or maybe even odd. Okay, good. So we just found that any Hamiltonian that commutes with the momentum and the winding symmetries are gapless. Well, that motivates us now to consider symmetric deformation of the XX model, because any deformation that we do has to preserve its gaplessness. And we can find the allowed symmetric deformation just by bosonizing the allowed terms in the family of fermionic models. So if you bosonize, H1, you'll just get the XX model term back, which is expected because we knew that when we fermionize this term, we got this H1. If you bosonize H2, okay, you get something that looks like this. And if you bosonize H3, it's starting to grow. And as you bosonize H with larger n, it will be including n plus 1 sites. You actually learn something quite interesting by studying this bosonization map. Namely, you may be curious, well, what do I have to, the image of what under this bosonization becomes the non-invertible operator D? Well, it turns out what becomes a non-invertible operator is this vector symmetry transformation times TA. And TA is this a Majorana translation that only translates the A Majoranas. Well, the general fermionic Hamiltonian we wrote down, it commuted with this first vector transformation by design, and it also commutes with TA. So then we learn, all of these qubit models that we get by bosonizing the family of Hamiltonians HF must also commute with the non-invertible symmetry operator D. So these momentum and the winding symmetries guarantee this non-invertible symmetry, and therefore also guarantee this lattice T-duality. Okay. So I want to end the talk by looking at a phase diagram with a Hamiltonian we build out of these terms I'm showing on the screen. And I'm going to commit a slight abuse of notation. I'm going to call the terms on the right by what they correspond to on the left here. So this is our Hamiltonian. This is H1, the image under bosonization is H1, but this is the XX model. And we have H2, which is including 3 qubits, and H3, which includes 4 neighboring qubits. So if we turn G2 and G3 off, we land on this point in the phase diagram, which is the XX point. And we label it by a star because we already know that the XX point in the deep IR is described by a CFT. So any point in the phase diagram that is described by a CFT in the deep IR, we'll label it by a star. And we'll also label the stars by the WZW CFTs they're described by. So what happens when I start to turn on G2 and G3? Well, I start to leave my XX model point, and I go to a phase which is gapless. And here, all of these phases are gapless, and I'm labeling them by this number big C, which is the number of direct fermions in the fermionized model. When you're exactly at the star points, the big C corresponds to the central charge of the CFT. So roughly speaking, big C tells you how many gapless degrees of freedom there are. So as I go around in this phase diagram, there's numerous phase transitions that we can hit. For example, if I go from the C equals 1 phase to the C equals 2 phase, I hit a transition at this purple line. And the phase transitions are labeled by the dynamical exponent. And it's interesting to note, all of these phase transitions have dynamical exponents of Z greater than 1. So all of these phase transitions are also not described by CFTs as well. And it's kind of funny, there's even a Z equals 5 multi-critical point in this phase diagram as well. Okay. So let's do a quick recap and an outlook. In this talk, we learned that many aspects of the compact boson CFT surprisingly exist exactly in the XX model. We saw there's a lattice T-duality. We saw that there's a corresponding non-invertible symmetry. There was lattice winding symmetries. There are Tufts anomalies, so on and so forth. And then we used that to motivate new symmetric deformations of the XX model, from which we found interesting new phase diagrams. And it's hard for me not to wonder if this is not just the tip of an iceberg. Throughout the whole talk, the compact boson CFT in the IR always had the radius r equals square root of 2. What about T-duality at other radii? What about T-duality when r is not equal to square root of n? Also, you can ask, well, what about other exact dualities like S-duality? Well, S-duality also has a corresponding non-invertible symmetry if the coupling constant is right. And there's also known qubit models in 3+1D that are described by Maxwell theory in the deep IR. In particular, models like quantum spin ice models. So do these quantum spin ice models actually secretly have a lattice S-duality? And then maybe less concretely, you can start to wonder, well, what is the general relationship between perturbative anomalies and algebras? Like we saw that the perturbative anomaly of the compact boson CFT is related to the Onsager algebra. What about perturbative anomalies of CFTs where the algebra is non-abelian, the current algebra is non-abelian? Or furthermore, what is, if there is one, the deeper relationship between exact dualities of QFTs and unitary transformations in quantum lattice models? We kind of started from the CFT, had an exact duality in mind, and found a unitary transformation that implemented the corresponding isomorphism on the lattice. But wouldn't it be interesting if we could find some isomorphism in a quantum lattice model and track what it becomes in the deep IR to find new dualities of quantum field theories? So thank you for your attention, and if anyone has any more questions, I'll be happy to answer them.
Okay, let's thank Sal for this very nice talk. Are there further questions? Maybe I can start with one. So did I understood correctly that all these other Hamiltonians are less and less local, right?
Yeah, that's right. As n increased, so 1, 2,
Yes.
3,
Yes.
so on, it
Okay.
becomes increasingly non-local.
Okay, good. And are they all mutually commuting?
Are they mutually commuting?
Yes.
No.
Oh, okay. Okay, thanks.
Yeah. Sorry. Yeah. The reason, the way that we found this diagram is not from the fact this is some mutually commuting Hamiltonian.
Okay.
It's the fact that in the fermionized model is exactly solvable, and we can use that to find the phase diagram of the bosonized model.
I see. Okay, thanks.
Can I ask a question?
Yeah, please.
Hi. So in the continuum CFT of the compact boson, you can change the radius by deforming with the product of the two currents of momentum and winding, right? Because you can see the kinetic term as J1 wedge J2. Is there something that you can do on the lattice on this route? Since now you have the currents for momentum unwinding.
Good. There is something you could do, but it's of different flavor. So if we go back to our XX model Hamiltonian, there are terms that we can add to it that will cause us to flow to different radii on the compact free boson. In particular, if you added another term, which is nearest neighbors of Z operators. So for example, you can add something like, plus delta. Delta will be a tuning parameter. Z at J plus 1. And for small enough delta, this will cause you in the IR to go to a compact boson, CFT, but at a different radius than square root of 2. The radius will actually decrease. But this term actually explicitly breaks the winding symmetry. Actually, it has to explicitly break the winding symmetry. And the reason is as follows. If this delta becomes large enough, you'll actually trigger a BKT transition, which on the lattice means you'll undergo some transition and you'll go to a phase that isn't gapless. It'll be gapped, but it isn't gapless. And that would contradict the gaplessness constraint that we found.
Great, thank you.
Can I also ask a question?
Yeah, please.
Thanks for the nice talk. And you are considering about gauging Z2s, and if we are kind of thinking about gauging Zn or maybe Z3s, are we going to have models on the qubit, or it is also you can also do it on the qubit?
Well, you can certainly gauge Zn in the qubit model. That's fine. For example, let's see. So here, well, what did the Gauss law look like? Well, it looked like this on-site guy with qubits on the nearest links. Well, alternatively, I could just go back to my definition of momentum charge. These all mutually commute. So I could just write the e to the I theta qm as a product over e to the I theta over 2 zj.
Yeah.
And I could try building Gauss's laws from those local e to the I theta over 2 zj's with theta at different, whatever your favorite root of unity is.
I see. Okay, thank you. Yeah.
Great. Any other questions? Yeah.
Hi. Can you
Hi.
see other type of non-invertible symmetries other than the Tambura-Yamagami thing from the lattice?
Good. So the operator D, good. So we could consider some ginormous family of non-invertible symmetries on the lattice. Here I'm showing some 2-parameter family just by multiplying D from the left by the winding symmetry operator and the momentum symmetry operator. But we know momentum and winding don't commute. So I can multiply it by a bunch of different alternating products of winding, momentum, and so on. But let me talk about this example here. If I take this example and I square it, I get the following fusion rules. And what's interesting about these fusion rules is you can deduce for which values of phi and theta this operator flows to one of the members of the S1 family of the Tambura-Yamagami fusion category. In particular, using that translations in the IR limit becomes this Z2 symmetry operator. Of this family, the ones that actually become Tambura-Yamagami are ones for which theta is equal to pi minus 2 phi. So when for Ds that aren't of this type, they'll flow to some non-invertible symmetry in the IR, which isn't Tambura-Yamagami.
Oh, I see. Okay. Thanks. So you can see some type of like the Treadlet defect in the paper by Ryan and Ifan, like at the KT transition point.
What transition point?
It's like the junction between the circle branch and the orbifold branch. There is some type of non-invertible Treadlet there, I guess.
So we can't see that, and that's because this lattice model just flows to R equals root 2. which is not at this point where the circle and orbifold
Oh,
branches
just
meet.
root 2. Okay, I see. Yes.
Yeah.
Okay, I see. Thanks.
Yeah. Thank you.
Are there further questions? Maybe let's stop the recording.